Okay. Okay. So can you see my screen now?
Yes, we can see your screen.
Okay. So thank you for inviting me to give the talk today. So I'd like to present a work from a PhD of the first student, Benjamin Gardner. It's a collaboration between our school, Laboratoire Navier, and the French National Radioactive Waste Management Agency. The work in this talk, I will talk about the hydromechanical behavior bentonite pellet-powder mixture. So this is a material that we will use in the context of geological radioactive waste disposal. So in the project in France, the plan is to store the radioactive waste in a depth of around 500 meter depth, and at this depth we have different tunnel and gallery to store the waste. So if we go inside in this zone, make a zoom, we can see that we need to we use bentonite pellet powder or bentonite based materials as sealing block, because this material have a very low permeabilities, like less than 10-9 meters per second, and with a high sealing pressure around 3 or 4 megapascal. And maybe you know that we can use some type compacted bentonite or other materials, but what is new here is that we use a mixture of pellet powder and pellet and powder mixture, because it's easy to pour this material inside the tunnel. So that's why we want to study this. So it can be a kind of compacted pellet, a big ball like that, and mixed with powder bentonite here, and you can pour without compacting the material inside the tunnel. So the size, the dimension of the tunnel is around 7 meters here. You can imagine that. So in our study, we want to study the behavior of this material in the lab. So as you can see that this material is very big, it's around several centimeters. So in the lab, we use a smaller pellet, around 7 millimeters only, and we mix this pellet with bentonite powder, and we study the hydromechanical behavior of this material. Why hydromechanical behavior? Because when you put bentonite in the tunnel here, water can go from the host rock and saturate the material, the bentonite. So the material will absorb water and will swell. So we will see the interaction between during the resaturation process and the swelling pressure developed during this process of these materials. So just a quick example: when we use this material in the lab, or what we did here is an imbibition experiments. So with this, so we can see here a cell. You can see here a cell, or where with a dimension of around 120 millimeter length, height, and width of around 60 millimeter. And you see here some small pellet, around 7 millimeter diameter pellet, mixed with powder here. And then we put on the side here sealing pressure, relative humidity sensor, and we inject water from the top, from the bottom, and we see how water migrate through the column to the top. And in this experiment, besides these two sensors, we use also a glass side on one face. So when we can use camera to see how through the glass side how water can migrate. So this is an example, a test performed on a mixture of 70% of pellet and 30% of powder. And within this, when we see that when water inject from the top here, we can see progressively water migrate from the bottom and to the top at the end here. progressively. And the measurement of, for example, relative humidity, we can see that the sensor at 20 millimeters, so close to the imbibition front, start to increase quickly and reach 100% quickly. Why the other take longer time to reach the reach 100%. So generally, this state can take around almost 1 year. You can see here, day is almost 1 year. And during this process, swelling pressure measurement measured at different depth here increased progressively. And the final value for this mixture reached around between 2 and 3 megapascal here, the final value. So the idea is that after this test, we want to try to simulate this kind of behavior. The difficulties here is that this is a mixture of pellets and powder. So we want to consider the granular aspect of this material. So we want to try to study we consider this material like a granular material. So we study first the behavior of one pellet, just like a grain here. So to start with this, we take just one pellet. So the pellet is very small, 7 millimeter here, and then we impose different suction to this pellet by vapor equilibrium techniques. And then first we measure the volumetric strain of this pellet when we impose suction to change the volume of this. And when we reach the equilibrium at each suction, we put this pellet under a mechanical press. And when we study the mechanical behavior, so in fact we compress the pellet and we measure the force as a function of displacement. So this relation, when as you compact a glass bit or no a bit, we can write. You can use theory to determine the elastic modulus of this pellet, this material, using this function, and also we can determine at which we can reach the maximum force. So is this a failure of the pellet? So of the pellet. So for example, for which fitting with this result, we can obtain that elastic modulus is around 500 megapascal for this pellet at this session. So within this approach, we can plot the volumetric strain of each pellet. Well, at the beginning, the suction inside the pellet is around 100 megapascal, and when we decrease progressively, is the suction here, the pellet will swell. So the swelling can reach up to 70% of volume. And then during this process, when we start at the initial state here, and when we decrease suction here, we can see that the Young modulus, so measured by the compression test, decrease, okay, with the suction here. And the strength, so the strength is the maximum force required to compress the pellet. So the strength, the pellet strength decrease also when suction decrease with this function. So here are all the experimental points that we obtained. So and then after that, we use a wide well-known model suggested by Alonso and for expensive soil, because we suppose that the pellet is very dense and we have only microspore inside. So micropore inside, and we suppose that the pellet is fully saturated at is an assumption. So in this case, we just use this function suggested by Alonso for micropore. Okay, and then we fit this parameter. We can see that within two parameter alpha and alpha beta here, we can fit at the same time all the parameters, all the tests at the same time. So we consider that this behavior is just the behavior of the micropore inside the compacted bentonite. After that, we study the behavior of different pellets inside a cell. So to do this, we use constant volume or isochoric cell to measure swelling pressure. So we put the pellet inside a cell here, and we put a big sensor here to measure the swelling pressure. So I remind that dimension of the pellet is around 7 millimeter. So we use here a bigger core, bigger SEM. The diameter of SEM is around 60 millimeters, so almost 10 times diameter of the pellet. But the height is only 30 because if we use another higher height, it will take longer time. So we try to reduce its height. And we use also a big sensor. The diameter of sensors is around 70 millimeter. So, and then we circulate vapor inside the cell. So it's a suction controlled vapor. Within that, we can impose suction inside the cell when we see how pressure will develop at each suction, at each level of suctions. So within this, here we have a picture of the pellet with powder here when we put all inside the cell. So this is an example of one test where we perform tests only with pellet without powder, so 7 without powder. So when we change suction here, but it takes longer time to, it takes around 100 days or 7 months to reach equilibrium for each step. So all the tests took around 400 days. When we decrease suction each step from the initial state, and then we reduce, here you have the value of suction here for each time where you impose. And the final value is when we inject liquid water. The final value here, the suction is reached around 0.25 megapascal. So we can plot this point here at equilibrium as a function of suction here. So we can see that when suction decreases, swelling pressure decrease progressively and reach the stabilization here. And we have several points because we did 2 tests here just to check the repeatability of the process. And now we go further. We use DEM simulation to check the properties of each pellet. We consider like a bit in simulation, and we at the first step we consider there are no powder, and we use simplified Hertz-Medellin elasticity and Coulomb fraction to describe the interaction between 2 pellets, 2 bits, and we perform to simulate these swelling pressure experiments. We put a large assembly of anisotropic compression in the simulation when we simulate the test. So I remind that the mechanical properties of each pellet it fit from the experiments on each pellet, on one pellet. So within this, when you perform the GM simulation, we can see here that when the suction decrease, swelling pressure increase quickly up to a very high pitch, so it's high value. And then after that, when we reach the collapse, or no, the strength of the pellet, the swelling pressure decrease progressively here. So the simulation show a peak, while the test here did not show a peak here. And then we did 100 simulation because it's DM, and then the size of the cell is small, so we can see that the last discrepancy of the simulation here. So what is important we can note after this simulation is that because of the size of the cell is small, so finally the test cannot be repeated with good repeatability here. So that is proved by the DM simulation. So that, and then another aspect is that the effect of the sensor. The sensor is the diameter of the sensor in this test is 4 times than the diameter of the pellet. So we show also that this can influence also the result. When you change the diameter of the pellet, the sensor, the result can change also. So that shows the difficulty of this test in lab because of the granular aspect of the material. The size of the pellet is quite high compared to the size of the cell and the sensor. But if you use a bigger cell, it will take longer time. I show here the test, which took 1 year or 2 years. So we do go further in the simulation. So now we try to add powder inside the particle, and we try to simulate this. So we realize that in fact we should add continuous domain. I mean, at the beginning when the material is dry, it looks like granular domain, but when you with the saturation, it becomes progressively continuous material. We should combine these two approaches, granular domain and continuous domain. So we combine GM simulation and simulation with like FEM simulation here. So I will not go further on this, but the idea is that with using this simulation, we can study the influence of granular structures, influence of powder content on this, and we suggest a very simple mode to go between the granular zone here and the continuous zone here, and we can within this we can fit quite good with a on a single set of parameters. We can simulate all the three tests we did here with different powder content inside. When you change the powder content, the surrounding pressure increase, and we can capture all this observation here. So I go to the conclusion here that this material is a binary granular mixture, so it's very difficult to study this. And at low powder content, the material behaves controlled by the pellet assembly, but with high granular material can be considered as continuous. We use GM, it can reproduce macroscopic behavior. And another conclusion is that the test is affected by cell dimension. As we propose a simple model that considers the same granular and continuous domains using a single set of parameters. Yeah, I thank you for your attention.